Greetings everyone, it's Professor Fiore. In this video, we are going to take a look at how you can create an RLC circuit model of a loudspeaker. Why might you want to do that? Well, you might want to see what the interaction is between your loudspeaker and a passive crossover network. Or maybe you want to do a more realistic analysis of a power amplifier. So you want a real world kind of a loudspeaker. In other words, one of these kinds of things, right? So here's a little woofer, a little 8-inch woofer. And you look on the back of it and it's going to say, this is a nominal 8 ohm value. And you might be tempted in your simulator, like here we are in Tina TI, to just use 8 ohms. And that's a starting point. It's useful, but it's not what this thing is. If you just put in 8 ohms, what you're really using is something closer to this. This is a 200 watt 8 ohm power resistor designed specifically for testing amplifiers, audio amplifiers. This is a pretty good size. This is maybe twice the size of a smartphone. You can tell just by the gauge of the wires here, right? Aluminum case. It's got mounts so that you can put it on a heat sink. That's pretty serious business. But this is a nice, well-behaved 8 ohm value. Just a big mahonkin resistor is all it is. But that's not what a real moving coil direct radiating loudspeaker is. All right? So what might you do? Well, your first pass might be to say, well, okay, I know the voice coil of my loudspeaker is, part resistive, part inductive, right? There's wire in the voice coil, so there's got to be a resistive element to it. But it's a coil, so there's got to be an inductive element to it. And you might wind up with something like this. Get out a DMM and you measure the voice coil, and it's 4.5 ohms, as an example. You could get out an LCR meter and measure the voice coil inductance, or more typically what you would do is you look at a manufacturer's spec sheet and they'll probably give you something like RE, which is the equivalent voice coil resistance, and LE, which is the equivalent voice coil inductance, right? So in this case, 4.5 ohms, 800 microhenries. All right, so what ends up happening here is at low frequencies, this sets the value, and as the frequency goes up, of course, X sub L goes up in accordance with our reactance equation, 2 pi FL. So as frequency goes up, this goes up, and the whole value goes up. So you have something that starts down here and then starts to increase as frequency increases. Not good enough. Simply not good enough. This is not going to cut it. Okay, it's better than just having 8 ohms, but it's not what it really looks like. What does a loudspeaker plot, impedance plot, really look like typically? It looks something more like this. And you can see this is not flat and then rising. There is this obvious big hump down here in the base. We can also see the phase response is not what it would have been predicted. If it was purely resistive, the phase response would be 0 degrees and it would just stay there. And if it was a resistive value with an inductive value, it would start at 0 and it would work itself up to 90, which this is not doing. You look at this thing and you're saying, sometimes it's inductive, sometimes it's capacitive. Only in a few spots is it actually resistive. That's kind of interesting, right? What the heck is this thing? Notice the peak on this can be pretty high. In this case, it's over 25 ohms, but this peak over here could be over 30 ohms, way above the nominal value, right? Here's your 8 ohms is right here. That's your nominal value for this. And by the way, this is just a single cone loudspeaker, right? This isn't an entire loudspeaker, that you would have in your home all completed in a box. This is just a raw frame, like, a woofer, maybe an 8, 10-inch woofer, whatever, all by itself, right? You start adding other things, put a mid-range on here, a tweeter, and so forth, you're going to get a pretty crazy looking overall impedance plot. Phase can go nuts too. But let's take one thing at a time, right? Let's just take a look at this one driver and see how we can come up with an RLC circuit that would mimic this. Might not be perfect, but something that we can use that'll give us a good basis point and that I can manipulate so that I can change, for example, where this peak frequency is. I can change maybe the width of this. What's this starting value down here? What's the valley? How quickly does this thing rise up? Where does it terminate? How high up is this? I want to be able to control all these parameters. All right? So that's what we're going to look at. Now, some things you can get off of a spec sheet. If you're lucky, you can actually get an impedance plot like this from your manufacturer. But otherwise, you can at least get some things. The RE value that you would get on a spec sheet, like I said, is this value back here. There's another thing called FS, the free air resonance. F sub S is this frequency right here. All right, that's this peak. Beyond that, is there a technique we can apply, right, to come up with appropriate values? So I'm going to show you kind of a little formulaic, a little flow chart kind of thing you can use to create a similar curve, a very close curve. And as a matter of fact, what I'm going to do at the very end is I'm going to mimic this exact thing. All right. Now, if you're saying, hey, wait a minute, I don't have this. I just have a loudspeaker. What do I do? Don't worry. I'm going to show you how you can create your own curve toward the end of the video. But for now, let's dive into this and see what we have for a model. Well, before I actually show you a model, it's important to understand some of the history. Back in the early 70s, early 1970s, there was a lot of work done in terms of making electrical analogs of a mechanical system, of a loudspeaker. So the idea was to be able to use electrical circuit analysis techniques to, quote unquote, solve this acoustical design so that we could more accurately predict things like bass response. Two of the big names associated with that were a fellow named Neville Thiele and another fellow named Richard Small. And that's where we get the idea, the Thiele-Small parameters that are often used to describe loudspeakers. They did a lot of work on this. And you can find their papers in the early and mid-70s, 1970s, in the Journal of the Audio Engineering Society. So what I've done is I've basically taken some of that material and sort of simplified it and pre-digested it and came up with some things that we can use. So the first thing I'm going to go to is what I would refer to as my level 1 generic model. So what we have up front is voice coil resistance, right? This is the RE, and the voice coil inductance, your LE, ideally. But we also have this other lump of 3 parallel elements. And if you're familiar with AC circuit analysis, you will recognize that peak that we saw, right? This peak is sort of emblematic of a parallel resonant circuit, where the impedance peaks at a resonant frequency, it falls off on either side, right? And that phase response would be typical of it. This inductive capacitive transition with a 0 degree phase shift, in other words, purely resistive, right at the peak, all right? Well, what do these things represent? In mechanical systems, things behave in ways that are analogous to the way electrical components behave. In other words, in a mechanical system, we have friction. And that can be modeled in an electrical system by resistance. We can model let's say the mass of a loudspeaker cone, and mass has characteristics. Mass has inertia, right? We can model that in terms of a capacitance. The springiness, the compliance of a suspension on a loudspeaker, the spider or the surround at the top, can be modeled as an inductance. In other words, from a mathematical standpoint, if you look at the original mechanical version of this and you write differential equations to describe what the motion is, and you turn around and you do the same thing with RL and C components, you come up with sets of equations that look pretty much the same. You just have different names for things, but the equations are basically the same. So since we already have a very well-established electrical analysis sort of technique, paradigm, we might as well just do that. We might as well just do the conversions. Now I can take something like this and put it in my simulator, and I can have a simulation of a loudspeaker. All right. So here's the way it works. We have a couple of equations. The reactance equation for the inductor, X sub L is 2 pi FL. All right. So inductive reactance increases with frequency, right? So if I've got frequency going this way and magnitude of the reactance going this way, I see this rising thing. Capacitive reactance is the exact opposite, right? It's 1 over 2 pi FC. So as the frequency goes up, the capacitive reactance falls, right? Exact opposite. So what we do to find resonance, in other words, where these two components resonate, if you will, that's defined as where the X sub L and the X sub C are the same value. So I just set these two equations equal to each other, and I solve for the resulting F0, which is the resonant frequency. And what we wind up with is this equation, 1 over 2 pi times the square root of LC. Unfortunately, there is no square root symbol that I could use, so I just took LC and I raised it to the 0.5 power, which mathematically is the same thing, right? Okay, so 1 over 2 pi times the square root of LC gives me the resonant frequency, all right? Now, here's your design guidelines. The R voice coil sets the DC level of resistance and the valley in the mid-range. In other words, if I go back to my Z plot over here, that sets this, which is typically very close to this. Right? This might be a little bit higher, but you're primarily starting here. Okay? Okie dokie. Now, LVC, the voice coil inductance, that sets what's happening at the extreme high frequency, right? So we had this peak, and then it rose up again. Well, that rising up again, where it actually starts to rise and how high it gets, is a function of this inductor. If you want it to rise up faster to get to a higher value, you need a bigger LVC value, right, according to this equation. So you put in a larger value here. Now, a starting value, because that's something that people want. You know, you want to start with something reasonable. These are sort of reasonable values to start with. You know, you're probably going to get somewhere in the 500 microhenry, 1, maybe 2 millihenry range for this inductance. This resistance is probably going to be 4, 5, 6 ohms, you know, somewhere around there. So that's where we're going to start. Okay. Now, when we get over to the resonant peak, that base resonant peak, there's a bunch of things going on. The first thing is, if we look at just the L and C at resonance, theoretically that goes to infinity. So what caps that resistance value is this guy over here, this resistance here. Basically, the peak is the sum of RES and RVC. In other words, getting back to our model, this value, this peak, which I can see is like 25.5 ohms or something like that, that's the sum of the voice coil resistance and that other parallel resistance. So what you would do is, since you would start knowing this value, simply subtract this, and that gives you the parallel resistance value, right? So here we go. I got 4.5 and 25. So that's 29.5. That's what the peak of that resonant would be. All right. All right. Now you just have to play with the capacitor and inductor that are in parallel in accordance with this equation to get the critical frequency that you need, the resonant frequency. And this is Fs, the free air resonant frequency that you would find on a spec sheet. All right. So you look up on the Thiele small parameters, Fs, that's the frequency that we're looking for. So as an example, all right, coming back to my plot, you can see, you know, here's 20 hertz, here's 30 hertz. We can see that just a little bit below 30 hertz, like maybe 28 hertz. So I have to manipulate these values to get that number through this equation, right? So my suggestion is, if you're going to start with these values, just pick one, like either the capacitor or the inductor. It doesn't really matter which. And just vary that one to get the frequency that you want. Basically, if you make either of these things bigger, you're going to drive the frequency lower, right? So, if you start with something and the critical frequency is, let's say, 50 hertz, and you need 32, okay, you're going to make one of these things bigger. And by doing that, you're going to get closer to your desired point, right? So just make one of them bigger. Now, what's going to wind up happening is that the Q, the width, if you will, of the resonant plot here probably won't be what you want. In other words, you might get something that's really broad that comes up like this, really pokey kind of thing. Or you might have something that's really tight, it comes in like this, like a really pointy kind of a plot here, right? Well, the way you deal with that is the ratio of CMES to LCES, all right? So you increase the capacitance and decrease the inductance to increase the Q. In other words, to make it sharper. So the easy way to do this is just come up with a factor. For example, if I want it to be tighter, if I want this sharper kind of curve, I might take my C value and multiply it by 1.2. Then I would take the L value and divide it by 1.2. By doing that, you have a factor of 1.2 divided by 1.2, which is unity. In other words, you'll wind up keeping the critical frequency constant. All right, so manipulate one of these to get the critical frequency you need. Then you sort of proportionately change the pair to get the Q that you need. All right? And you'll wind up with something, a little trial and error. I mean, it's not going to take like days, but you get a calculator, and of course you just put this in the simulator like Tina here, and you can plot this. All right, I'll show you that in just a sec. But eventually you'll get this. All right. The final thing is dealing with this high frequency end. All right, what's this? Where does this terminate? How quickly does it go? Where does it start? Does it start back here and start to rise like this? Is it kind of pokey and it goes like this, right? So you manipulate this, the LVC, to adjust that particular value. Now, it might not come out exactly the way you want. It might be one of those things where, it terminates at too high a value, but it starts at, too late of a value. You just can't get it, right? In other words, the curve maybe has this kind of a slope, and what you need is something that's flatter, something like this. It's not rising as fast. So what do? Well, we can go to a slightly modified model here. Now this extra R value, RSH, it's there to set an upper limit on how big the X sub L value can go to. And it's essentially modeling what's happening with the eddy current losses in the magnet. And this may work for you. There is, the same set of things going on here. The only thing is you can manipulate that terminating value by setting an appropriate value of RSH. What I have to warn you about is if you get a little too greedy, let's say, this curve can kind of come up and then drop back down. So you might get it perfect here, but then it's going to die out over here. And the phase response can start doing some weird things. It can start falling back down towards zero. In a case like that, I suggest you go to model number 3. So here I have another inductance in series with that shunt resistance. And now, by playing with these two things in accordance with this, you can control what that slope is doing. All right, so you can modify the slope with this. A good place to start, I would say, would be to set this LVC2 equal to your original value that you started with. And just a note of caution, I know it's labeled LVC and LVC2. I'm not talking about a dual voice coil loudspeaker, like something you would use for a sub. Okay, a dual voice coil. That's not what this is. This is just a secondary reactive element to help get us a nice curve. All right. Okay, so now that you have this, I mean, how are you actually going back and forth and checking it? Well, what you do is, here's the easy thing. You take your model and you just hook it up to a current source. Hook up a sine wave current source and be smart about it. Just set the sine wave current source to 1 amp. Why 1 amp? He said, right? Why 1 amp? Curious. Because voltage is equal to current times impedance. So if I set the current to unity, then whatever the resulting voltage is out here at Vx, that's the ohmic value that I have for this whole thing. So all I have to do is just plot Vx. Bingo, we're done. All right, so let me go up here and I'm going to do just a plot of this sort of random model 1, level 1 system that I have. Okay, so this is going to be a frequency response plot because I want to see what the Z is doing, which is actually the voltage, right? But it's going to reflect the Z of this network. All right, so I'm going to start this at 1 hertz. We're going to go up to 10 kilohertz, which will be sufficient. I am just going to look at the amplitude of this, see what we get. Now, there's a couple little tricks, at least in TINA. It all depends on the simulator that you're using. TINA, when you do a frequency response plot, a Bode plot, it defaults to what you would expect for a Bode plot, which is a decibel axis over here. But I don't want that. In fact, I want a linear axis. And I want it to start at 0 and go up to a reasonable value, maybe, I don't know, 50 ohms. Okay, so here is my curve. And you can compare that back to what we had for our Z model, right? Matter of fact, let me take this and scooch that over a little bit. You can kind of see where we are. All right. So we have basically the same shape, right? Now the scale here isn't quite the same, my frequency scale. So the shape isn't perfect, but I mean this, right? But it has all the ingredients that we need, right? There's a peak, there's various values. So I can see that this peak is coming out here. This is up around, looks like 34, 35 ohms. All right. And that should correspond to, right, the 2 resistor values that we had. Well, there's 4 over there, and I got 30 there, right? So 30 plus 4 is 34. That's what we should get right here. Matter of fact, let's be complete about it. Where's our peak? Yep, there it is. All right, 33.997. Okay, 34, right? So this happens to peak out here at about 35.4 hertz. So that would be your critical frequency, basically. The resonant frequency, the FS. Okay? And when we came way down here at the low end, right, there's the 4 ohms that we expect to see. All right, that's the voice coil resistance value. All right, so like I said, we could kind of monkey with this. If I changed the inductor over here, the voice coil inductance, like let me drop this from 700 to 500 microhenries. Okay, and I am going to redo this. Let's move him over here a little bit and spread him out a little bit. And once again, I am going to have to change my axes. All right, so this part should not have changed. Let's compare the two. And they haven't. But look what's happening out here. All right, so I made the inductor smaller and the exabel is smaller. So we see the curve drooping down, right? Okay, so far so good, right? The other thing that I mentioned was this guy sets the peak, right? This RES sets the peak. So let's go in. I'm just going to increase that. Why not? Let's try this one. So what should we get for a peak, right? We should get 35 plus 4, or 39. And once again, I have to change this. A little tedious, but hey, there it is. It would be nice if it could kind of read your mind. Alrighty, so here's where we were, here's where we are. You can see, yep, there's 40 up there, that's 39. I'm not even going to bother getting the cursor out. Okay, so I can adjust that. The other thing I mentioned was you got to move the frequencies around. So let's crank up CMES over here and go to, oh, let's make it big. I'll make it 400 mic. We'll double this out. Guess what we're going to do first? You guessed it. Change this. All right, where were we? Okay, so look at the peak. Where is the peak? Okay, that peak is in the mid-30s, right? There's 10, 20, 30, 40. So we're in the mid-30s right here. And our new one is in the mid-20s now. Okay. The other thing I said was we can control the thickness, the width of this, by controlling the ratio of these two. So what I'm going to do is I'm just going to use a factor of 2 here, just because I can do it in my head. I'm going to divide CMES by 2, so I go from 400 to 200. But then I'm going to multiply LCES by the same amount. All right, so I should get the same critical frequency out of here. But the thickness of this is going to change. All right, the Q value, as we would say. High Q is narrow. Low Q is broad. All righty. And just to compare everything on an even keel. And let's go back and forth, right? So here's where we started. And then what I did is I dropped the C value and increased the L value, which, as I said, should give us a fatter response curve, in other words, a lower Q. And that's exactly what we see. That peak has not changed. Right? This up here hasn't changed. This down here hasn't really changed. How we get there, of course, has. But there you go. So you can now play with these things and get a good idea of, a loudspeaker that's realistic. All right. Okay. So as I said at the beginning, we could start with something like this and say, hey, can I make a model that's similar to this? Well, I did. I happened to needed the level 3 model. I needed the model, the level 3 model here, because the slope at the high end was a little touchy. But the way I approached this, right, let's just kind of recap here. I looked at this peak and I said, all right, that's looks like about 25.5 ohms or so. This down here, I actually chose, because I had a full data set for this thing, I actually chose the value that is on the data set, the Thiele small parameters, which is I think 4.5 ohms if I remember correctly, instead of what I see here on the graph. My choice. But nonetheless, no, it was 6.5. I must be confusing that with the preceding one I did. All right, let me just double check that. Yeah, 5, 6. Yeah, that is 6.5. Okay, my bad. So I got 6.5, and I needed to get that 25 and change. So 6.5 and 19 gives me the 25.5 I was looking for. Once I had that established, I could start monkeying with this to get the critical frequency that I needed, and eventually start working over here to get the high frequency end that we needed. So let's go and take a look at the resulting curve. Bingo! Now, as a matter of fact, you know what I'm going to do just to show you this, because I didn't show you this before. Let us do an amplitude and phase. All right, this is more funner. It's more funnerer. Now, this is where it gets a little squirrely. Trying to get this thing to look exactly the same. Trying to line this up just about right. So that's scale, that's 30, 30. Oh, stupid me. I forgot to do this. Alrighty, now how does this match up? So I have to bring this guy up here a bit, because I want to get the heights to be about the same, right? I want this axis and this axis to be pretty close. Well, that's pretty close. It's not exact. What about the width? It could be a little narrower. All right. So it's a little bit squished, but pretty much, right? So here's the peak over here is, there's 20, there's 30. It's a little under 30. It's like 28 or something like that. We see that here. We've got this 6.5 ohms here. As we go up, this one is limited to 10K, whereas this one goes up to 20K. So here's the 10K is up around 20 ohms, a little over 20 ohms. So mine is a little bit higher, but not too much higher. So there's a little bit of deviation here, but it's not too bad. Down around this area, I would say from a few kilohertz down, it is pretty much spot on. If you look at like here at the 10 ohms, 10 hertz, right? Here's 10 hertz, 10 ohms. It's the same point, right? Out here, as we're coming down here, same kind of point. Everything looks pretty good. The phase response looks a little funky, but that's just because the scale on it is so messed up by comparison to this one. So we're going to have to bring this into, I believe that was 180 and 180. All right, so that looks pretty close, right? Compare this guy to this guy. You can see how we're coming up. Crossing through zero resistive right at the peak as expected, then flipping back up here, a little over a kilohertz, 2 kilohertz, somewhere in that region, crossing back through and then continuing right up. All right. So really the only place I had a little bit of a deviation was up here. Okay. This is not quite right, but this is a woofer. And quite honestly, trying to model this thing out to, 10, 20 kilohertz, of modest utility. All right. Okay. So what do we wind up with here? All right. We wind up with a fairly simple kind of model. Bring him back here. Oops, hit the wrong button. Sorry about that. Fairly simple kind of model, and this is really the most sophisticated one, right? My sort of level 1 is this one. It's got 5 components, and you can make a pretty nice system, right? Pretty nice simulation with this. All right, in the beginning I said, hey, I know you're worried about the fact that maybe you don't have a plot. How do I make a plot? Okay, well, theoretically, you could use this circuit, right? I mean, this would be your loudspeaker, okay? Practically, this is not going to work because, like I said, this is a 1 amp current source, and you probably don't have a 1 amp current source, variable frequency at your disposal. So what do you do instead? Well, you do this. You model a current source with a voltage source and a really big resistor. Ideally, you want a sine wave generator over here that can get you maybe 10 volts peak, okay, good size signal. And the resistor you're going to need should be at least an order of magnitude, preferably 2, larger than the biggest value you're going to get out of here. So I'm going to say at a minimum a k ohm, 10K would be better. So this combo right here, the voltage source and the resistor, basically behaves as a current source. So you feed that current in, and again, this is your loudspeaker, and you just start taking measurements. All right, so the first measurement you probably want to take, you might want to just get a DMM and measure the voice coil resistance, right? Get that RVC value, get that out of the way. Then you drive this with your function generator, plug this into a scope, a digital scope, and you can just see the waveform. You'll just see the sine wave, and you can measure what that voltage is, but you'll know what the current is. So if you had 10 volts peak and you got a 10K, you divide that out and that's a 1 milliamp current, right? So whatever you see for a voltage on the scope, you just remember, okay, that's with 1 milliamp of current. So I can just use Ohm's law and determine what that is. Now your resonant frequency, Fs, will occur at a peak. As you change the input frequency, you're starting down below, like maybe 10 hertz, and you start cranking that frequency up. You got to do this kind of slowly. You'll see that voltage grow. That sine wave will get bigger and bigger and bigger and bigger in amplitude. And then it'll start to fall off again, right? So wherever it maxes out, that's Fs. Another thing you can do is take a second probe, put one on the generator, and when the two are perfectly in phase, that would mean the circuit's resistive. When they're perfectly in phase, that's another way of defining where Fs is. So you record that frequency. And then what you do is you just pick a bunch of frequencies on either side, 2, 3 frequencies below Fs, 2, 3 frequencies above Fs, and that'll be enough to give you data for the shape, right? The shape of that curve. How thick or thin is it, right? What's the Q? Then do a couple of higher ones, like 1 kilohertz, 2 kilohertz, 5 kilohertz, 10 kilohertz. That'll give you all the data that you need for the high end, in other words, this guy over here, or the more fancier version of it. Write down your numbers. Now if you want to, you can get out a piece of graph paper and plot it, but you don't have to. As long as you have the values, you know where to start. You know all the hit points, so to speak. In other words, having done that, what this point is here is, what this point here is. You have a couple of data points out here, so you can figure out how thick this is. You have a couple of data points out here, so you can determine that slope, right? Just how high it goes. Beautiful, right? Now, you might be tempted, if you don't have a scope, you might be tempted to say, well, I'll get a DMM and I'll measure the voltage that way. I have to caution you about that. Unless you have a fairly high-end DMM, it's not going to accurately measure AC at higher frequencies. A halfway decent meter will go up to about 1 kilohertz for AC. Some of the bargain ones, they only go up to maybe 100, 200 hertz before they really start to die on you. So they start to get really inaccurate. You're going to have to spend some money to get a DMM that will give you the kind of accuracy that you want, have enough resolution, up to 20 kilohertz. The scope is the obvious thing to use here. Possibly you could use one of the applications. They have these digital scope applications for your computer using your sound hardware, your audio hardware, input-output. So theoretically you could do that, but I have to warn you, the output probably won't be big enough. You can get one of those virtual function generator apps. So you would have to use some kind of amplifier to crank that signal up so that you can drive the loudspeaker. You still need a pretty good sized signal out here, right? And that's not going to give you 10 volts peak, no way. So you'd have to come up with something to kind of modify that. But in any case, that is how you can do it. So, hey, now you have, right? Now you have a model, and you can take that model and you can put it in your simulator and you can do all kinds of fun things with it, right? Okay, that's good. Hope you had a good time on this one, and we'll see you next time.